Hello everyone, in this particular video let's try to solve the questions from JEE Advance 2025 from the chapter Coordination Compounds. Okay, so I asked two questions in paper 1 and paper 2. We'll discuss these two. Okay, that's how we will solve 2024 questions year by year. I thought of solving, so we'll continue this series like this chapter wise. I will try to make videos. Okay, third they were asking about correct order of wavelength, maximum of absorption band in the UV region for the given complexes. So instead of asking about energy, they were asking about wavelength in order to make you confused, because in coordination compounds most of the questions we will solve regarding energy, right? E is equals to hc by lambda. E is inversely proportional to lambda. This relation you know, right? If the energy is more, then wavelength will be less. So if you have an idea about this relation, you can easily solve this question. Here one thing you can observe is that for all the given complexes, coordination number is 6 only. This leads to octahedral crystal field splitting. Okay, so how the splitting takes place in the case of octahedral? This is the 3D, right? So this is the 3D. It splits into eg and t2g orbital. This is eg, this is T2G. Okay, and also one more thing that you need to know, here we will be comparing based on the strength of the ligands. If the strength of if it is a strong ligand, then if it is a strong field ligand, then weak field ligand above. See here one more concept that you need to understand. Here the different types of ligands they have given. Okay, so we will compare the energy levels. Here the strong ligands cause larger splitting. Okay, larger splitting means more energy means less wavelength. Okay, less wavelength. If it is a weak field ligand, the energy gap between T2G and EG will be less. So you can say less energy gap or less energy. Okay, this is the less energy gap which leads to more wavelength. So this is the simple thing that you need to know. Now just check the options and see, I have also mentioned over here the spectrochemical series, right? Here this is the strong field ligand and here it is a weak field ligand. Okay, so you can see here they have given cyanide, cn, nh3, ammonia and water and chlorine. They have given these ligands. Okay, so what is the order of strength of the ligands over here? So you can see this chlorine is weak field ligand, and then what comes? Water. Then after ammonia, then cyanide, right? So this is the order of strength of the ligand. I have told you, if it is a strong field ligand, there will be more energy gap which leads to less wavelength. So that's how you can just correlate the idea. Simply reverse the order for the wavelength. So as it is a cyanide is a strong field ligand among all the given ligands over here, it will be having more energy gap. More energy gap means less wavelength. So this will be having less wavelength over here. So you can see here also they have given this is having less wavelength, and here also they have given less wavelength. You can eliminate these two options. Okay, next one, this is the uh, I mean, as compared to this chlorine and water, this is the strong field ligand. So it will be having less wavelength as compared to remaining two. So that's why next comes this one. Here they have given here in the next one they have given ammonia and water. As you can see, water is a weak field ligand as compared to ammonia, right? So it is a combination of both. Like here the coordination number is 6 overall, and they have given two different types of ligands, but it's fine. You can simply compare with this strength of ligands, right? Here in the last compound weak field ligand is there, means weak field ligand means there is a less energy gap means more wavelength. So wherever this chlorine is there, that will corresponding to higher wavelength. Okay, fine. So this option is the correct answer. You can see why this is not the answer. Here they have given this is having the more wavelength. This is not the case, because ammonia is also a strong field ligand, so energy gap will be more, which corresponding to less wavelength. Let me summarize this. what I have explained you. Here they have asked about correct order of wavelength. Okay, so this is the point. Here energy is inversely proportional to wavelength, right? And here every complex is having coordination number as 6, means it is a octahedral crystal field splitting, right? How in octahedral complexes how splitting occurs, this is how splitting occurs. And you just need to compare the energy gaps. That energy levels depends on the ligands. If it is a strong field ligand, there is a more energy gap, so it more energy means less wavelength. If it is a weak field ligands, there will be a less energy gap, which leads to a more wavelength. So that's how we have compared. We have written the strength of ligands here. Whatever they have given over here, the ligands, the strength of ligands order is this. So based on this, we have simply solved this question. Okay, so I hope you have understood this question, and if you have any doubt, you just let me know in the comment section. Okay, so we'll try to solve this question also now. Here they were asking the sum of the spin only magnetic moment values in Bohr magnet, and here they have given two complexes. See, the first thing that you could do is that you need to write the electronic configuration. In order to write the electronic configuration, see here, if you have an idea about these electronic configurations, you can simply, I mean, it helps you a lot. Okay, see, scandium, what is the atomic number? 21, right? This is simply organ 3d1 4s2. What you will do, you just add the one electron in the d shell bus. This is like 3d and 4s2. Okay, just take care of this chromium and copper having the electronic configuration as 3d5 4s1, and copper is having 3d10 4s1. Okay, because of half filled and full filled configuration. Here they were asking about magnetic moment. What is magnetic moment? This is the formula, n of n plus 2, and the units are Bohr magnet. Okay, so here what is n? N is the number of unpaired electrons. See, I'll tell you one thing. If they ask about number of unpaired electrons and all, if you want to find out how many unpaired electrons are there in that particular complex, just use the crystal field theory. Okay, that I have discussed over here. The how splitting takes place in case of octahedral, and you need to know how splitting takes place in case of tetrahedral also. Maybe I'll be solving questions. These two complexes also octahedral only, so the same splitting takes place over here. Okay, and based on the ligands, we will try to fill the electrons. Okay, that we will see now. Here, so here, I mean, like, what is the oxidation state of this manganese? Over here you can find it, X minus. Bromine carries -1 charge, so 6 into -1 is equals to overall charge is -3. X minus 6 is equals to -3, which is +3, right? So manganese is there in +3 oxidation state. Actually, what is the electronic configuration of manganese? You can see here. This is organ 3d5 4s2. So just remove 3 electrons from the outermost shell and write the electronic configuration for Mn3 positive, which is organ 3d4, right? Just remove 2 electrons and 1 electron from this d orbital. Now, how this is having coordination number as 6, means octahedral splitting takes place over here also. And here bromine is a weak field ligand, we have seen that, right? And now how the splitting takes place, let me explain it over here. So this is a 3d, right? 1 2 3 4. The overall thing is that we need to find out the number of unpaired electrons from for both of these complexes. Okay, I am trying to do the same thing. Here the splitting takes place like this. This is T2G, this is EG. As it is a weak field ion, what happens? The energy gap is low, that we have discussed, right? So here in this question also we have discussed, if it is a weak field ion, the energy gap will be less. So what happens? First we will try to fill the each electron with the in the T2G and EG, then pairing start takes place. You can say here pairing is greater than delta naught. So so that's why here pairing won't takes place directly. Okay, that is the thing that I wanted to mention. Now let's try to fill the electrons. Here 4 electrons were there, 1 2 3 4. How we will fill over here? First try to we will fill each orbital with 1 electron, and then pairing start takes place, because it is a weak field line, so energy gap will be less. But jump is easy. Okay, just see, if you are getting confused where pairing takes place, where it won't takes place, just have an idea about this thing. Okay, see, I have told you, in case of weak field ions, the energy gap is less. If the energy gap is less, the jump is easy, right? You can easily jump. Let's say, for example, this is a one step and this is one step. There is a less gap over here. So you can jump directly without even thinking, right? So that's how. And in case of strong field ion, what happens? The energy gap is more. So here jump is not easy. Here jump is easy in case of weak field line. In case of strong field line, jump is not easy. So pairing takes place over here. So I hope you have understood these 2 points. These are the things that you need to understand in coordination compounds, because most of the question they last from these topics. Okay, so here we have understood there how many unpaired electrons were there now. Four, right? So there were four unpaired electrons further. We have understood. So now let's try to find out this spin only magnetic moment, which is 4 of 4 plus 2. How much? 4, 6 are 24. 24 means 4 for the 16, 5 5 are 25. It is in between 4 square and 5 square, right? Nearly you can take it as 4.9 Bohr magnet. And here they have given the range as 7.5 to 7.8. Let's see, do we get that or not? Okay, so now let's talk about this complex Mn Cn 6 3 negative. So if this video is going slow, you can switch to 2x speed and watch it. Okay, so here the thing is that coordination number is 6, and here the cn is a strong field line we have seen. And you might get the doubt how we'll get to know which is strong field line, which is weak field line. Solve few of the questions, you will have an idea like, acha, this is we will see these frequently, this cyanide, ammonia, and this halogens all are like weak field ions only. You will get an idea. Okay, so no need to mug up and all, you can just have an idea. So cyanide is a strong field ion. I have told you here, in case of strong field ion, what happens? The energy gap is more. Due to the more energy gap, the jump is hard, so pairing takes place. So that's why what happens over here, let me first we need to write the electronic configuration, right? So let's try to write the electronic configuration over here. Okay, here what is the oxidation state of this manganese? Here also it is plus 3 only. So this is also same organ 3d4. But here the thing is that here a pairing takes place. Here didn't, due to the strong field ion. Here the energy gap, let me draw it a bit like upper, so that you can have an idea that the energy gap is more. Okay, so here the due to more energy gap over here, what happens? What happens over here? Pairing takes place. It won't jump, right? So here 1, 2, 3, 4. So here pairing takes place. It won't jump over here. 1, 2, 3, 4. So now how many unpaired electrons were there here? 2, right? So now you can easily find out spin only magnetic moment by using this formula, 2 into 2 plus 2, which is 4, which is root 8. This is in between 2 square, 2 twos are 4 and 3 threes are 9. So you can roughly take it as 2.8, or you can take it as 2.9 also. Let's see what is the answer we will get. If we get the answer within this range, that will be fine. Okay, so we need to sum. They have asked about sum only. So 4.9, let's take 2.8 or 2.9. Let's take 2.9 also. Like, let's see, 9 nines are 18, 4 5 6 7. See, we have got 7.8. Or see, if you take 2.9, you will get nearly 7.7. That is also accepted. So I hope you have understood these two questions. These are the two questions they have asked. See, these two questions are easy only, right? If you have an idea about, if you have revised properly this coordination compounds, you can easily solve this question. It's just about, see, the important things that you need to know, like what are the strong field ligands, what are the weak field ligands, and how the splitting takes place in case of octahedral uh, complexes, and in case of tetrahedral complexes. If you have an idea about all these things, you can easily solve these questions. And yeah, I'll be solving, like, see, I'll try to solve like 2025 questions, 2024, like that. Year wise I'm going to solve the questions. And yeah, that's it. Just take care, and if these videos are helping you out, just do let me know, because some sort of motivation I'll get to create even more videos. And so yeah, that's it. Just take care and bye.